the Mentimeter when I don't show the QR code. And now it's time to dive right back in. And I'll start with something that in some way we've already worked with quite a lot. On the right-hand side, you see some table with a load time series here given in gigawatts, an on-wind, so onshore wind per unit capacity factor time series, a solar per unit capacity factor time series. So that's nothing really new. But today we want to bring these time series somehow together. It's something that we didn't do in the first lecture, where we looked at the characteristics of the individual time series, like repeating patterns, what are the frequencies, what is the duration curve, and things like that. But today, in a very conceptual way, we want to put them together, because for a renewable energy system to work, or any electricity system in general, you need to balance the supply with the demand. In a highly renewable system, most of your supply will come from something that's variable, wind and solar. So in some way, we have to figure out a way to align these two. And we won't always get a perfect match. So in this thought experiment that we'll work with in the upcoming slides, we're going to do the following. We're going to scale the onshore wind and solar capacity factor time series with some capacities alpha and beta, so that on average, we cover the load. So that and it doesn't really matter what alpha and beta we choose, as long as the average generation that we can get, or you could also say the total generation over the time period that we look at, it meets the load. So this criteria doesn't take account any of the time series. It just sums up or averages over the whole time series. And that will give us a so-called mismatched time series in where we see, well, we have some demand, and subtract from that alpha times our time series wind T, or beta our time series solar T. So it's really just our capacity factors scaled by some capacity, which will give us units in gigawatt, which is the same as the load. And this will tell us about the mismatch at any point in time T, while in total we produce as much electricity as is consumed. So we'll have some periods where the demand will be larger than the wind and solar generation, and we have some periods where the demand will be smaller than the generation, and in this case, our mismatch time series would be negative. I said mismatch time series, just the mismatch between load and generation. The term you will find in the literature for that is the residual load. Residual load is because we have in principle some load, subtract some generation that is varying that we have from that, and then we maybe have some residual demand that we need to meet with other means. Could be, we'll talk about a few options, but could be other power plants or storage or some other measures. So the residual load is negative when you have an excess in renewables, and positive if you have kind of a gap in the renewables. To illustrate that, I brought here 1 month of time series. We'll start with a case where I have scaled the time series so that it's only it's 100% wind system. And here we have some periods like these, where you have just more wind generation than your load in black. And you have some periods here throughout the mid of the month where your wind generation is lower than the demand. So this is, even though I actually scaled it in a way that the average for this month balances out, even though we have that balancing out, we don't have the electricity available at the same time. So we have some periods of shortage and some periods of excess. And this relates to the beginning of the course, where we looked at the individual time series, this mismatch, depending on what your resource mix is, whether it's wind heavy or solar heavy, can be highly influenced by this resource mix. So for example, if I now switch to a 100% solar system, you still have, in kind of terms of energy, so area or integral over this time period, you have it balancing out to 0. But you have, again, periods of shortage, periods of excess, but the pattern looks much different than before. You have here this daily pattern that reflects just the daily frequency of the solar generation. And before, we had this kind of multi-week balancing, or multi-week variability of the wind playing a big role. So what do we do in this case? So one thing that comes up, well, we could do storage, right? We could store in periods of excess, and we could bring the energy then to periods of shortage. And I want to introduce that concept on a very kind of basic level, or with an analogy of the bathtub. I think I mentioned that in response to one question a couple of lectures ago, just to illustrate that there are different parameters that we need to think about when we want to understand what storage capacity is required. So somebody could maybe ask the question, oh, well, how much storage do we need? And then there's not one value that we can answer this question with, because there's different things that can play a role. There's one question, well, how quickly do I need to absorb excess electricity? And that's the charging power. How quickly can I put power from the grid into a storage? And that would be, for example, driven by this difference between the generation and the load in the periods of excess. And I have the same in the opposite. When I have a period of shortage, well, how much do I need to supplement the renewable generation to bring the generation from this shortage to the actual load? I also have to think about, well, how quickly can I turn the whatever I store back into electricity? And then another question would be, well, how big does my storage need to be? How much energy does it need to hold? So you can make somewhat of an analogy with a bathtub, where you have kind of three main design parameters, or three capacity parameters, where one is how much energy can the storage hold? How much water does the bathtub hold? How quickly can I put water into the bathtub? That would be the charging equivalent to the charging power capacity of the storage. How quickly can I put electricity or energy into it? And then I also have a drain, which represents the opposite. How quickly can I get water out of the bathtub into the drain or somewhere else? So there's some analogies like this: the bathtub volume, the energy capacity, the maximum inflow rate, the charging power capacity, the maximum outflow rate, the discharging power capacity. And these are somewhat all design parameters. Yeah, these are kind of, you buy a bathtub, you buy an energy storage with these parameters. And then there are a few operational characteristics of the storage. For example, the equivalent to a water level in a bathtub would be how much energy is currently in the storage, and that's typically described as state of charge. And then the inflow and the outflow is how much do you actually put into how much water currently flows per minute or something like that into the bathtub, and how much flows out. And these are other parameters that we control by operating the energy storage. So it doesn't always have to be, for example, take a battery. It doesn't have to consume power at the charging power capacity. It can also be lower if we control it in this way. So one thing that this bathtub analogy doesn't account for, and what we'll also skip for now, and we'll just introduce that in a couple of minutes, is, well, in this analogy, we don't lose any energy. We don't lose any water, which is for energy storage, you have some conversion efficiencies of bringing water into the bathtub, and also when draining, you cannot make everything useful. For example, it could be something like a water loss in the pipes that go to the bathtub and out of the bathtub, something like that. Or if you leave water too long in the bathtub, it evaporates and you have less water level in the bathtub. Okay, but I'll stop with the bathtub analogy now. It's a bit of a constructed example, but maybe it helps some people to understand the idea. But let's go back to our residual load. And here I put in a full year. So before we looked at just one month, and here we have a full year of residual load. This is really just kind of the sum of the generation and the load, or to be precise, it's the demand minus the renewable generation. And here for this data set, I used some mix of wind and solar. So it's not 100% wind, not 100% solar. And again, in the periods where this time series is positive, we have a shortage. So we have some demand, for example, for storage to discharge into the grid. And then you can also see that in some periods, or in many periods actually, there's a negative residual load, which means we have more electricity supply than we have consumption. So that would be an opportunity to, for example, charge a storage. How do we get from, and our goal here is to understand how much storage do we need in terms of these three parameters that we just thought about. And neglecting losses, two of them I can already see from this graph. I can look at the peak, the highest residual load, and the lowest residual load. The highest residual load would be the maximum amount of electricity I need to be able to put into the grid at some point. So that would be my maximum discharging capacity, that would determine it. And then the same for the charging capacity. I would look at this period here where my residual load is the most negative, has the smallest value, and that would determine how much my charging capacity. That's a rough idea. There can be economic reasons to just go here in reality, to not cater for the most extreme case and let some renewables be spilled. But remember that one of the constructions at the beginning was that we actually scale the wind and solar capacities just to the level that we have enough. So if we have perfect storage, we can't waste any electricity. So we actually have to go to the peak, because otherwise we can't meet all the demand in this constructed example. Leaves us. And you can also see, you can already see some nice things about it. For example, that in this example, your charging capacity needs to be much higher than your discharging capacity. So that leaves us with one more parameter that we need to calculate, namely how much energy storage does this storage need to be able to hold. And for that, we need to build something like an integral over this residual load time series. So it's a bit of a challenge at the beginning. We only look at one year of data, but you can see maybe the first few days, there's an excess of renewables. So because the residual load is negative, in these periods, we would charge our storage. So if we think of an integral that moves kind of from left to right, then at the beginning, we fill up the storage. So our state of charge will somehow go up. And then we have this one segment here where we are actually discharging. So a state of charge of the storage, the energy that it holds, it should go down again. And then we charge again, and then we discharge again. And when we just do this, build the integral, or if we have discrete time steps of hourly data, just build the cumulative sum of the residual load time series. And again, we're neglecting losses. We get something that looks like this. So and here we again see things from the example that we start with charging the storage, then we have a short period of discharging, and then a period of charging followed by discharging again. And we have that throughout the full year. And you can see here in this example, we have relatively strong seasonal component. Yeah, we're discharging here throughout the late winter month, early spring, charging again throughout the summer. Kind of, we have a rough profile. But if you look closely, you can also see some more spiky elements here. And that could be, for example, daily patterns of the storage, but they don't affect the overall energy that is stored too much. Okay, I did one magic trick here because I figured out a way, an initial state of charge so that we never go negative. If I had started with a 0 state of charge, so here we started with roughly 10,000 gigawatt hours. If I started at 0 and just built a cumulative sum, I would have ended up with negative values. It's meaning that there wouldn't have been enough energy at the beginning of the period to bring us through the whole year. What I did is, and I mean, that's also kind of constructed, but it just, whenever we're looking at a limited period of data, we need to make some assumptions about the initial state of the system. And one way would be here in this example to look retrospectively. I build the cumulative sum and then look, well, how far negative does it go? Because that will tell us, okay, how much does the storage, how much energy would have had to be in the storage at the beginning of the period to never go negative. So here we have one point in the year where we have exactly a state of charge of 0. And this is because I scaled the curve in that way so that it starts with a value so that it exactly goes to 0. It's constructed. What you see in modeling, in many cases, you can see this as well, that you make some assumption about the initial state of charge. In many cases, you have something like a cyclicity constraint. So typically in energy capacity expansion models that we're going to look at in a couple of weeks, you will have 1 year or maybe 2 years of weather data. And then you say, okay, it's kind of limited scope. And I have no idea what the initial state of charge should be. So I'll just let it be cyclic. So I say whatever the final state of charge in the model is, it should also be the first. And in that way, I kind of close just my model, even though the time horizon is limited. That's something that you can do. It's also constructed, of course, it's a model after all, but it at least ensures that the model does not benefit from some magic appearing energy that you put in the storage at the beginning of a period. So what would be super bad from a modeling perspective is, well, I modeled 1 year of data, but I put the state of charge at 100,000 gigawatt hours. And at the end of the year, it can go to 0. And it doesn't cost anything because it's stored energy, right? It must come from somewhere. That would be a huge modeling error because you're giving the model 100,000 gigawatt hours of free energy. So the SOC must be a non-negative quantity by definition. And in this case, we have to choose some form of initial SOC. And we can do this by shifting the kind of the cumulative sum that we initially calculate from the residual load by the minimum value. And that will typically be a negative value. Otherwise, you don't have to shift anything. And then from that, you can read the energy storage capacity, how much energy this storage would need to hold. And in this case, maybe somewhere around 26,000 gigawatt hours. It's just the maximum of the state of charge curve that would then determine our capacity. Okay, don't look at the next slide yet, because that's maybe a brainstorming question on the Slido. So we'll go through two cases and collect a few ideas. I mean, I mentioned storage already, but in general, there's a few balancing actions that you can do to deal with periods of shortage. We'll start with shortage, and then afterwards we do the and afterwards we'll do the axis. Okay, right. So in periods of shortage, um, so yeah, storage. Well, I stop the contributions. They can cross things out. So yeah, storage. You can you can discharge a storage in periods of shortage. Precondition, of course, is that the state of charge of the storage needs to be high enough. Yes. We could import from other regions. So maybe all the analysis we did was for one region, and we could import it from neighboring regions. That's a very good point. Load shedding, yes, it has, of course, economic implications to shed load, just reduce the load by force. And curtailment would be something, curtailment would be kind of reducing the output of renewables or load curtailment. So that's kind of load shedding example as well. We could ramp up dispatchable generation, yes. So if we're not fully decarbonized yet, we could, for example, run a gas power plant here, for example, or some renewable fuel in the future. That's a good point. Storage, we have power reserves, I guess, is power plants. Load shading, yeah, load shaving, yes. Load management, interconnection relates to imports. And then I see maybe basically efficiency improvements may be more a long-term action, but short-term action could also be if it's not load shedding, it's maybe just load shifting or demand side management, kind of moving your demand to an adjacent hour where your where your supply looks a bit better. Okay, so let's quickly do also the other side. What do we do in periods of excess? Oh, not that. Okay. Okay, from what I've seen so far, there's a lot of duality. Like if you import in one period, you can export in the other period. So let's show the responses. So we have, so if we import in periods of shortage, then we maybe can help others in periods of export and in periods of excess. When we export electricity, we can charge the storage, yes. We can curtail renewables, yeah, not just not use the electricity. We can make fuels out of that. So that's kind of related to storage. We maybe store energy in form of hydrogen and kind of turn electricity with water into hydrogen. And that could also kind of, if we have demand side management, we could also increase the load when we have reduced it in previous periods, or when we anticipate a shortage in an upcoming period. Okay, very good. The next example will be in a while. So yeah, so I think we have these cases covered. So then the next question is, what do you have like we're now clear on what alternatives are available, but which of these options are actually good? If you think about gas power plants or other fossil fuel power plants, then your backup generation may cause additional CO2 emissions. So yeah, maybe not. Let's see what other options we have available. Curtailment, well, we want renewable electricity, low carbon electricity. So if we waste it, then it's kind of, let's not waste it if we can avoid it. And that leaves us with potentially some better options, or some options that we at least should scope. So using electricity storage to shift energy from times of surplus to times of deficit, the demand side management that was mentioned by some of you, as well as another way of balancing in space. So storage and demand side management somehow balance in time because they move demand or energy from time to time, and also balance in space with transmission grids over large areas. And that relates to the import-export mechanism that some of you mentioned earlier. So it might be that in kind of Denmark it's windy, whereas it's in southern Germany it's not windy, and then in some other period in southern Germany it's windy, in Denmark not so much. And then you can use the transmission grid to really balance the differences in renewable availability. Okay, if we look at kind of the storage concept in math, very simple math, then and have this image of kind of energy moving in time through our model, then we have some constraints on the charging. So we make some decisions about how much a storage should be discharged with a dt, how much it should be charged. And both of them, they should be positive quantities and should be within the respective capacity limits. So we have a capacity limit for the capacity for the discharging, a capacity for the charging. For some storage technologies, these are actually the same, but not in general. And then we also have some variable to keep track of the state of charge, the energy level, ET, of the storage, that is also limited by a limit. And then if we look at how the state of charge ET evolves over time, we would always look at, well, what was the state of charge in the previous period? We have some inflow from charging, some outflow from discharging potentially, and that is what we carry over into the next period. So we have some form of iterative relation between the state of charge, charges in the different periods, depending on what operational action we take. I think that is probably very clear. But something that we've left out so far is the efficiency or the conversion efficiencies in storage. There's basically three conceptual efficiencies. You maybe have some efficiency loss from charging the storage, some efficiency loss from discharging the storage, and maybe also have something like a self-discharge. And yeah, these can be added into these into this energy continuity, or sometimes also said called storage consistency equation in this way. So kind of let's start with a self-discharge. Maybe some of you left a phone in a drawer for a long time, maybe an old phone, and started to restart it. Didn't work, although it was maybe fully charged at the beginning. So you have some self-discharge, usually in storage. Could be for hydro storage, for example. You have some evaporation of the basin, for example. Um, Also for batteries, you have that. Also for other storage technologies. You maybe have some charging efficiency. If you have a chemical storage, you maybe say you want to make hydrogen. Your efficiency of going from electricity to hydrogen with adding water, your conversion will not be 1-to-1, but maybe say 50, 60, 70% or something, depending on how far you look into the future. So whatever electricity you consume, so that, let's say that is CT, you will not get as a benefit in the state of charge. You will just get a fraction of that, and that is the efficiency. And then you have the kind of opposite for the discharging, that whatever you take out of the storage, you don't get as much electricity out of it. If you have a hydrogen turbine, for example, or a hydrogen fuel cell or something, there's also an efficiency loss associated with that. And then for hydro reservoirs, you maybe have some additional elements in these equations, because you have some natural inflow, natural increase in state of charge from the upstream river, or in some cases, you maybe want to, if it was very rainy, for example, there's a lot of water, you maybe need to spill the water without actually using it in form of electricity, and that would be corresponding to reducing the state of charge of the storage without actually producing electricity out of that. Okay, so I thought maybe we do a concrete example, or you do a concrete example. And let's see. So I removed the solution, or I left it in and tried to quickly switch. But we have a storage, and we know that at the start of hour 1, we're looking at 2 hours in total. We have a state of charge of 200 megawatt hours. So you have some energy already in the storage. In the first hour, there's an excess of renewables. We charge the storage with a rate of 125 megawatt of electricity consumption with an efficiency of 80%. And then in hour 2, we have a shortage of renewables. We discharge the storage to supply 120 megawatt of electricity, and this with an efficiency of 60%. So we actually need to take out more out of the storage. And then in the hour 2, there's one more addition, is that the ambient conditions, so the kind of environmental conditions, make the storage unit lose 1% of its energy. And that's only the case in hour 2. And the question, and there's a slide again, is what the SOC would be at the end of hour 2. And maybe, yeah, you just try to calculate that within, I don't know, there's not maybe 3 minutes or something like that. Let's see how much time you need. But let's calculate that. Okay, so I hope not everyone looked up the solution on the slide, but I think most are correct. So it's 97 is the correct answer. It's 100 is the correct answer if you don't factor in the standing loss. And this you can see in this chart here, illustrated. So basically, the first column here is the start of hour one. The second column is the end of hour one. And the third column would be the end of hour two. So within hour one, we start with an initial state of charge of 200. We charge with 125 megawatts of electricity, out of which 20% go to the losses. So we're actually charging with 100 megawatts. So at the end of hour one, our state of charge would be 300. And then we're discharging 120. And that means we take out of the storage 120 over 60%. So we divide by 60%. And then we have also 1% of the 300 as losses. And that means, so 120 divided by 0.6 would be 200. We have additional 3 that go into the losses. So we end up at a state of charge of 97 megawatt hours. And if we neglected the standing losses, it would be 100. Would just be subtracting the 200 that we take, for example, out of 200 megawatt of hydrogen that we would take out of storage, for example, to put into electricity or convert into electricity. Okay, so I have here a picture of different storage technologies. And not sure if you know all of them. Not sure I know all of them anymore. But I have one task for you to pick the heat storage technology. And I think it's set up in a way that you can just kind of point somewhere on this image. There's a couple of different storage technologies. Each of them represents one. And there's at least one heat storage technology in there. And I can tell you so far that the majority is wrong. Okay, good. So there's actually 2 heat storage technologies in there. And this here would be something classical fuel storage, gas storage, for example, that you can see today. Then this here is battery storage. It's in Australia, South Australia. This is a kind of gravity storage concept, looks fancy. This is compressed air storage concept. This is a classical hydro concept. This I have no idea anymore. And these 2 are heat storage concepts, but on 2 very different levels. So this is a heat storage concept from a company called Rondo. They do really high temperature heat storage at around 1,000 degrees Celsius. It's kind of, I'm not sure how much of that is in operation, but it's kind of an idea to electrify really high temperature industrial heat for melting things and making glass, for example, things like that. And this here is a storage concept that you see, for example, in Denmark, although I'm pretty sure this image is not from Denmark, it's too hilly, is where you store hot water basically over a season. So they have district heating networks in Denmark where you could, for example, heat up water with solar electricity over the summer and then use that heat in the winter to supply heat to homes. And it's really basically an isolated well in the ground. Okay, so but the goal is not really to go through each of these different storage technologies. Maybe at some point in the group work later on, you have the option to work through a couple of them. But I just want to make the point that kind of different types of balancing needs, different types of residual load curves, different profiles, different renewable mixes of wind and solar, they might need different types of storage. And why different types of storage? Because they can vary in their parameters, and some may be more suitable to storing energy for a short amount of time, but being very cost efficient at dispatching a lot of electricity quickly. And some technologies may be more suited, like for example, storing chemicals. It's very cheap for storing it for longer periods, but it's potentially inefficient to convert that electricity to that carrier. So here just kind of battery as one example with very high efficiencies, both for discharging and charging, but relatively high cost for kind of the size of the bathtub, so to speak, which makes it relatively unattractive for storing a lot of energy over a long time. But it is very cheap given the efficiency and also the cost per kilowatt for charging and discharging is relatively attractive for balancing at a short period of time. Then we also have, for example, hydrogen storage is just one example of a chemical storage where we have relatively high losses from the conversion, both for charging and the discharging, but depending and high cost per kilowatt of charging and discharging. Electrolyzers have become very, very expensive. Also, a hydrogen turbine has some cost, whereas the cost per euro per kilowatt hour can be quite low if you manage to store it underground, but also much lower than for the battery if you still have to do it in overground steel tanks. So that it's more suitable for really storing big volumes of energy for weeks to months, but where you don't have to cycle through charging and discharging many times. And then pumped hydro, kind of the classical technology, it depends a lot more on the geography. So just make this example. Consider you have kind of 1 kilowatt of power capacity, different energy capacities. If you take a battery for a 4 kilowatt hour battery, you're landing at 770 euros in cost. Whereas with the hydrogen, you land at 2,600. But then if you look for kind of longer term storage, a larger bathtub, then your battery becomes suddenly much, much more expensive than compared to the hydrogen storage, which doesn't scale that much with the energy capacity. So battery storage is lower losses, mostly cheaper for short-term storage periods, and hydrogen or some form of chemical storage is exactly the opposite. You have high losses, but that's traded off against being able to store cheaper for longer periods, and both can be, or even a mix of them can be cost effective depending on your balancing needs. If you have a strongly seasonal profile in your generation and relatively constant demand, then you need some form of long duration energy storage. Different technologies, how they're used for different purposes. Pumped hydro batteries and small scale thermal storage, for example, in households, or demand side management, which I also put into the category of storage because it's modeled, when we model that, it's modeled in a very similar way. They would be more suitable for these daily variations, and then for the longer term weekly seasonal variations, you would be looking at some form of chemical like hydrogen, carbonaceous fuel, or hydro reservoirs where you can store larger amounts of water at altitude, or these examples of kind of seasonal heat storage if you can live with kind of relatively low temperature heat, such as in district heating networks. And kind of this kind of classification, these charts, I won't go into too much detail, but where you basically have one axis for how much energy the storage can hold and what the duration of discharge is, and that's just another expression for the relation between the storage capacity and the energy capacity. It's kind of max hours, it's always also called. It's just a value for how long could the storage discharge at full capacity to run from full to empty. So if your storage has a capacity of 1 megawatt hour and 1 megawatt of peak capacity, your duration of discharge would be 1 hour. And then you have here really these kind of underground chemical storage at the very top right end, where you have really long duration of discharge and high storage capacities. And then you have things like superconducting materials and capacitors for really short-term kind of in periods below what we're going to look at in this course. In this course, we're going to look at the most at hourly resolutions, and there the fastest paced technologies are batteries. In terms of batteries, I don't know if you know this website. Is another nice example of kind of data visualization, data science. It's done by RWTH Aachen. It's called Battery Charts, and gives you not only this chart, but an idea of the current status of how much battery storage there is in Germany at the moment. And you can see the regional distribution. You can see the major large-scale batteries, for example, here in Northern Westphalia, somewhere in the north of Germany, but then also bulk of home storage that is much more distributed. And in terms of kind of large-scale grid-connected battery storage, we're now at roughly 2 gigawatts of mostly lithium-ion batteries, but 16 gigawatt and 24 gigawatt hours of battery storage. So coming back to this duration of discharge or max hours of the storage, if we look at the aggregate of all the batteries in Germany, we have a max hours of 1.5. Because to discharge the 24 gigawatt hours of batteries at full capacity, at 16 gigawatts, it would take us 1.5 hours to run from completely full to completely empty. Okay. Any questions so far? So otherwise, we're going to enter this new segment here. And this one is a bit of a mix between a renewable resource and a storage, because often the hydro comes with some storage capacity. And that just means we can, for reservoirs, for example, we can choose sometimes when we let the water pass to produce electricity, and sometimes we can even pump water back up to the upper basin, for example, when the electricity prices are cheap. So there's always some storage component. And again, you can, for example, go to Global Energy Monitor. The data set that you worked with the nuclear data in your assignments also exists for hydropower around the world. You can see kind of the green bits are those that are operating, and the red to orange ones and the yellow ones are those that are planned and under construction. And when you look at the kind of globe at the moment, in terms of development of new hydropower, then really China, Southeast Asia, India are hotspots for that. If you wonder I wondered what this big blob is, and it's actually planned a new hydropower plant of 60 gigawatts in China. It's meant to be operating in 15 years or something, but there's another bigger one blob here, that is the current largest hydro plant in the world. Just to give you an impression, it's in China. It was opened in between 2003 and 2012, and the height difference here is 181 meters, and this width here is 2.3 kilometers. The difference in the water level between the lower basin and the upper basin is 80 meters, and there are 32 700 megawatt turbines and a total rating of 22.5 gigawatts. So Germany's peak load may be somewhere 70 gigawatts. Just to give you an impression for one of the dots in this chart. But as I mentioned, so if you look at the development of and significance of hydroelectricity around the world, we see most of the developments in the past 2 decades in Southeast Asia, not so much development in other world regions, but there are some regions, mostly relatively poor countries, for example, here in Africa, but also other regions in the world. Also some very rich countries like Norway and Switzerland and Austria that have relatively high shares of hydropower in their system. And that, of course, just depends on the geography of these countries or the fact that they just don't have a lot of electricity consumption or production overall. If we take a closer look into hydropower in Europe, how it's distributed, that you can see in the left chart, and you can see different color types for different types of hydropower plants, namely the run-of-river plants, basically plants that don't have work with that don't store, that don't have a big dam, for example, that stores water for a longer time. You see that quite prevalent in the Alps or in Scotland, for example. You have reservoirs, hydro reservoirs. So these are basically also run-of-river plants, but they have they have potentially a dam and also the option to just store more water in the basin behind them so that you can delay sending water through. And then there's also pump storage. It's what is most prevalent in Germany. We have 2 basins, and you run water down when you want to generate electricity and pump water up if you want to kind of store electricity. Good. So, but generally speaking, there's not a lot of hydro development in Europe anymore. But the reason I showed all these statistics is that we want to understand a little bit more the resource of hydro and how to determine that and what data you work with in this case. And the most important thing is you need to figure out how much water you have flowing through your river. How much water you have flowing at the location where you would like to extract the water. So say that's a given. Let's forget about the rest. I will explain that in a moment. But one important parameter is, well, what is the time series of the water flow at the location where I want to extract the water for the turbine, for the generation? And for that, I have to look at the geography. I have to look at the height differences, and I have to calculate the so-called catchment area. So this is the area where, when you have precipitation in this area or a well in this area, this water will ultimately end up in this point, unless it evaporates, of course, or goes into the groundwater. How do you calculate that? Maybe look at the other picture here. So say this is our power point, or the location where we're considering a power plant. Then we would kind of go orthogonal to the inclination and then walk along the ridges. Because if you were right of the ridge, the water would go into another valley. And if you're left of that water would kind of go to the left, and then through different paths, to different kind of, not sure what the word is, but kind of smaller parts of the river, it will end up in this location where we're considering the power plant. And of course, that is an important consideration because the amount of water is basically your currency for how much electricity you can generate. So it makes sense to choose a location where your catchment area is quite large. So that's one important criterion. And so the data that you need here is, of course, kind of the kind of elevation data set. And once you have that, you can go to some like the ERA 5 data set that we also looked at last week, where you have data on wind speeds and solar irradiation and so on. You also have data on the so-called runoff. And that is just a muddled parameter that includes mostly precipitation, but also things like snow melt, minus the evaporation that goes into the atmosphere on this land, minus the water that goes into the groundwater and doesn't end up here. We have two elements here that you combine, the kind of weather data to look at, well, how much water is there in this area, and then to calculate the area itself, you would need to look at elevation data. Okay, so that's one important consideration. How big is your catchment area? How much water do you have here? But then let's focus about this part. What happens once I have the water? What is another siting factor? And for a hydropower plant to have the best effect or best conversion from water, and basically you're using gravitational energy, you need also a height difference between, or yeah, it's an important consideration to have a height difference between the extraction point and the location of the turbine. So you would send water through a penstock, so-called penstock, just basically a pipe somewhat, where you have at the bottom a powerhouse with a generator where the kind of water spins a turbine, and then kind of let the water go into the river again. And probably you've seen somewhat this kind of formula at some point. The power that is available is basically, it depends on your flow, your cubic meters per second that go through the penstock. The Okay, I should be back online now. Sorry about that. The battery of the microphone died. Excellent. Good. I guess this was what the questions were about. Good. Okay. If there's any remaining questions, then let me know. Okay, so where do we stop? Okay, so some water we need to reserve for the environmental constraints. There's some amount of water that we cannot take, even if it's available. And if the water is naturally below that, then of course, I mean, there's nothing we can do about it. We're not interfering. Then it's also fine. But this is water we need to reserve for the natural river flow. We don't want to prepare everything for the floods, so we cut away some high flows and will only use up to this rated flow level. So we cut away some other water, and that water would also just go through the natural river flow. And in some cases, the turbine might not be working with very low water speeds or water volumes, water flows, for similar to the wind turbines that need a minimum wind speed to operate. So out of the flows that you would have available in principle, there might also be a minimum flow that has to be deducted in this duration curve. And then what you're left with is this wide area here. That is the water that in principle you have available for generation after taking into account environmental constraints and technical economical constraints of the turbine. So what this would result in terms of time series, that, I mean, you can disentangle this flow duration curve again into a time series, and then you would have basically this flow deducted from it and the maximum value kept to this value. Okay, different types of turbines I mentioned. This is not a technical course about introducing different types of turbine, but just so that you have seen it, there's different types, and they are used for specific applications depending on the head and the flow rate, so the height difference and how much water is going through. And what you can often see is, you can see charts like this, where you have kind of the flow rates in cubic meters per second on one axis, the head on another axis, which kind of both translate into some capacity, which would help you choose the best kind of operating regime for the different turbines. So we can go through one example to wrap up this lecture, which I don't know if this is large enough, but I think for the example it should be. Which of these turbines would you choose for this run-of-river plant if you have a head of 100 meters and a flow of 10 cubic meters per second? Okay, so that was too easy. You all got the correct answer. How do you read this? Flow, you look at 10 meters per second, go up until 100 meters, and you end up in the Francis regime. The only thing that would have made this a little bit more difficult is that these axes are on a logarithmic scale. Okay, anyway, I would say we close for this session and maybe take a break until 10 to 6. And then we continue with the networks lecture.